Okay, welcome back. We're going to be starting our final unit today. This is our last unit in grade 10 applied, so we're pretty excited about that. Our last unit is actually the most important because it's going to be talking about quadratic relations. What the heck are these quadratic relations? What do they mean? What do they look like? How do we graph them? And ultimately, in grade 11, whether you choose the college or the mixed level program, it's all quadratics. You're going to be starting with quadratics, and then you'll have a little bit of trig, but the majority of that course in grade 11 is quadratic. So let's get introduced to what the heck a quadratic is and what it looks like. So a quadratic equation, like all we've ever seen before, just to take a minute here, the only thing we've ever graphed between grade 9 and 10 so far has been y equals mx plus b. And we've called this a linear equation. And what makes this linear is that we have a coefficient in front of a variable to the degree of 1, and then there's a y-intercept at the back, and we call that b. And right now I'm going to introduce another equation to you. This equation is going to look very different than this y equals mx plus b, but not really. If we look at this new equation, y equals ax squared plus bx plus c, doesn't this part right here look like mx plus b? That's because it is. We've just got different letters there. We have a bx plus c. Okay, now what we're adding to this linear equation ultimately is this new part right here, this x squared. This x squared is what makes something or turns something into a quadratic. Okay, so anytime we see a leading coefficient, we have a coefficient other than 0 in front of that x squared, because then it'll make it a 0, and we have a highest degree of 2 with that leading coefficient, then we're dealing with a quadratic relationship. Okay, so quadratic relationships can just look like an x squared, can look like an x squared with an x and a constant behind it, can look like positives or negatives. It doesn't matter as long as we have that x squared at the front. Okay, and something to note too, and we'll get more into detail with this as the unit goes on, and ultimately you're going to be doing this a lot next year. You're always going to be writing your equations from the highest degree to 1, 0. So you're always going from the highest to the lowest when you write your equations out for your degrees. So this quadratic relationship that we're going to be talking about is going to be a relationship which is non-linear. Non-linear simply means not a straight line. Now you've done this before in grade 9. Okay, so non-linear graphs in grade 9, you had a graph and it looked like that. A little squiggle, something, right? You did distance time graphs, which were made up of linear equations, but overall were nonlinear functions. For us, our quadratic relationship is going to take a form of a U-shaped curve that we're going to call a parabola. Okay, so this is a new important word for us right now, parabola. Okay, parabola, parabola. So looking at these two graphs below, we could see the straight line that we're used to, which is y equals mx plus b. This line we would call a linear function. And now we're going to introduce a nonlinear function, but it's got a special name for us, and it's called a quadratic. And it has the equation ax squared plus bx plus c. Okay, how do I know this is a quadratic? I see that x squared. How do I know this is linear? Because it's only got the highest degree of 1 in that y equals mx plus b. And these are the shapes that we're going to be producing, these U shapes, which we call parabolas. So first let's take a second here and look at some equations and then determine whether they're linear or quadratic. So if I look at the first two equations here, y equals 3x plus 7 and y equals 4x, do you see any x to the power of 2? I don't. So these are all x's to the power of 1. This means that this is y equals mx plus b, y equals mx plus b, which means that they are linear. And if I look at these next two examples over here, I see an x squared and I see an x squared. I've got a 1x behind it. I don't have a 1x behind it, but that's okay. I've got a 5 behind it. Do I see an x to the power of 3 or x to the power of 4 or anything freaky like that? I do not. These are totally different. Cubics and quartic functions, we don't know, but I could trick you by saying, what are they? And you would just say that they're nonlinear functions, because I don't know what they are at this point. All I know is that when I see an x to the power of 2 as the highest degree, that these are quadratics. And what type of shape do they form? Parabolas. So that's how quickly on our CPT we can tell by looking at, or in this unit, by looking at an equation whether it's linear or quadratic. Just look towards the highest degree in that function, and if it's a 1, it's linear, and if it's got a 2, it's quadratic. Now in your CPT, I ask you to determine whether we're dealing with linear, nonlinear, or a quadratic. Now for this, we have to go back to grade 9. And in grade 9, we learned something called first differences. First differences to tell whether something is linear or not is when we subtract from the bottom up. So let's quickly review that by subtracting from the bottom up. And if we have a constant value the first time we subtract, then we're dealing with a linear equation. If they're not constant, then it's nonlinear. So you're going to take out your calculators and we're going to just subtract from the bottom up. 8 minus 5, 3. 5 minus 2, 3. Now here's where you got to be careful on your calculator. 2 minus negative 1, 3. So this is my first difference. And because they're all the same, they're all constants, they're all going up by 3, which is actually my slope, going up 3 over 1. But anyways, because that is my first difference is all constant. What does that word constant means? It means the same. That this is a linear equation. Cool, we know that from last year. Now let's look at another example over here. We could subtract from the bottom up. Again, do the same process. Negative 1 minus negative 2. Be careful, the signs are kind of weird here. Then negative 2 minus negative 3. Then negative 3 minus 2. Then then 2 minus 7. Do I have them all being the same in my first difference here? No. It's just that these first two are the same, these second two are the same, but they're not the same overall. So is this linear? No. This is nonlinear because they're not constant. Now let me look at this last example here. We're going to subtract from the bottom up. We'll do 27 minus 9. We'll do 9 minus 3. And we'll do 3 minus 1. None of these are constant. So again, we're dealing with a non-linear function. But now I want to draw your attention to something else. A new table. Look at this table up here that I've written in. Your x's are negative 2, negative 1, 0, 1, 2, and your y's are 4, 1, 0, 1, 4. Now you can kind of see a pattern that's going on with these y's, can't you? That's okay if you don't. If I were to graph this though, it would tell me right away that I'm dealing with a quadratics because it's going to be producing a U shape. So let's do some exploring here. Let's do our first differences. Let's subtract from the bottom up. 4 minus 1, 3. 1 minus 0, 1. 0 minus 1, negative 1. 1 minus 4, negative 3. So when I subtracted my first time, they're all different, as you can see. But now we're going to learn something new. So in grade 9, you did something called your first difference by subtracting and seeing whether they were constant, and that would tell me whether it's linear or nonlinear. We know that a quadratic is a nonlinear function, correct? Now let's see something. What about if I subtract a second time? What if I do a second difference? So I'm going to take the values that I just subtracted and I'm going to subtract them again. 3 minus 1, 2. 1 minus negative 1, 2. Negative 1 minus negative 3, 2. Wow. See what happened in my second difference? They're all constant. They're all the same. This is telling me that when I do a second difference, if they're the same, that I'm dealing with, you guessed it, a quadratic. Why does that happen? Well, I'm going to explain this the easiest way that I know how. When you had your linear equation, you had an x to the power of 1. Y equals mx plus b. Remember that? So therefore, with the first time you subtract, if all the differences are the same, then that's linear. Now, with a quadratic, you have an x to the power of 2. So that means the second time that you subtract, if they're all constant, you've got a quadratic. And that's what we've got in this case. So looking at these two examples and comparing them, we can see that if the first time we subtract, they're all the same, great, it's linear. If you subtract the first time and the second time, and there's nothing going on, there's no constants happening, then they're nonlinear, like these two examples. But this last example here is special because if I subtract once and it doesn't work out, and I subtract twice, and guess what it does? They all become constant, then that's a quadratic. So going forward in grade 10 and in grade 11 to tell whether a table of values is linear, nonlinear, or quadratic, we're going to have to subtract not only once, but twice. Now this example is in your CPT. You'll have to perform this task of subtracting twice to tell whether the function is linear or quadratic. And that's hopefully going to help you with that section of your CPT. Now with the quadratic, we've got a pretty special shape here. It's called a parabola, and there are some important features on this parabola. So first of all, with the parabola, we should always be putting arrows on the ends, whether it's pointed up, or a parabola can actually be pointed up or down, it doesn't matter. And those arrows indicate that this parabola will go on forever. So the dark lines here, the black lines, are my y and x axes that we're used to. So that's where my grid, where my Cartesian plane is happening. Then I've got this quadratic, which is this U-shaped graph that we've seen is created by the equation y equals ax squared plus bx plus c, and it has constants in the second difference. So this U-shaped graph forms from a table of values from an equation, and it has some important points. The most important point is the turning point of this graph. So when reading math or reading a graph, I always start off on the left. So here's the left side over here. Follow the graph, it's going down, and then it reaches this very important point. We call that the turning point, which has a special name. It's called the vertex. And then from going down, all of a sudden now the graph is going up. So this point, we call that the vertex. And that vertex is a point that consists of an x and a y value. So if I asked you for the vertex of this graph that's given to you above, you would say that the x value is at 1 and that the y value is at -4. And that would be my vertex. Now this vertex has a line that runs through it, and this line, which is indicated by the red dotted line, cuts the parabola in half. The line that cuts the parabola in half runs right through the vertex. You can see that, right? The red line splits that parabola in half through the vertex. And when we're dealing with a vertical line, we're making sure that that vertical line has the equation x equals and then a number. So in this case, it'll be x is equal to 1. That's where the vertical line occurs because it passes through 1. So what's the name of this vertical line? We call it an axis of symmetry, which is actually down here for you if you need to know how to spell it. So axis of symmetry is the line that cuts the parabola in half. Now, do you notice something special about the value of this axis of symmetry? That's right. It's the x value from my vertex. So this x value from the vertex is the axis of symmetry. Now, another important point is this one right here, where the parabola crosses the y-axis. What did we call that point when we were dealing with a linear equation? That's right, we called it a y-intercept because it's where the graph intercepts, which means crosses, the y-axis. And it's not going to change here. We're going to call that the y-intercept. That y-intercept is where the graph crosses the y-axis. And now we're going to look at these two important points. And it's not where we're crossing the y-axis, but it's where our graph crosses the x-axis. So what do you think we call that, where the graph crosses the the x-axis? That's right, we call it the x-intercepts. Now that's where our graph crosses the x-axis, sometimes at 1, 2, or even no points. So now going down here, we've got some key terms: vertex, our max or min value, axis of symmetry, and x-intercepts. The only one which we haven't covered is the max or min value. The max or min value, actually, this is a very good one that we should have covered here. It's the y value of my vertex. So by looking at this graph right now, it's pointed up. This vertex is the lowest point. The lowest point is at -4 for y. But if I had a graph that was open down and was a parabola, this vertex would have a max. So right now I'm dealing with a minimum in this example, but I could have a max. And it's ultimately the y value of the vertex. So now we can fill in some definitions. So we'll read the first one here. The vertical line that passes through the vertex, well, right away, vertical line passes through a vertex. The only one that's a vertical line that passes through a vertex is the axis of symmetry. It's the coordinate x in our vertex. The x-coordinates of the points at which the parabola crosses the x-axis, so we cross the x-axis at the x-intercepts. The greatest maximum or least minimum y value, the y value which comes from my vertex, which we just explained, is the max or min value. And that obviously leaves D, the point at which the parabola changes from decreasing to increasing or increasing to decreasing is the most important point, is the vertex. So that concludes the first lesson on parabolas.